Well, greetings everyone. Last October I was invited by a family to go through the estate of a friend of mine who passed away a few years ago, and they were going through some of his old electronic equipment and decided to give me a substantial part of it. And I'm just wanted to show you some of it right here that I'd like to do a restore on in the future. And the one I'm particularly interested in is this little RCA sweep generator right here. Now, I've never owned a sweep generator before, and I'm looking forward to seeing if this thing even works. What I have right now is this old genometer, and it's just a straight RF generator with a AM modulation in it. But this RCA will sweep a 455 kilohertz IF band and a 10.7 megahertz FM band. So I'm kind of excited to see if this thing will really work. So I don't think we'll do a full-on restoration of it unless it needs it, but let's go put this thing on the bench. And before I power it up to see if it even works, I really want to bring it up slowly on a variac over here and a dim bulb, just to be sure there's something not shorted inside, and I don't want to destroy anything that I can't obtain parts for. So if you're interested in this, stand by. We'll open it up and just give it a quick look over to see if there's anything out of the ordinary or anything that needs to be replaced before we power it up, like a shorted capacitor or leaky filter capacitor or something like that. But yeah, we'll get busy taking it apart, and if you want to, we'll go through it together and see how it works. Well, let's go ahead and get the cover off this thing. Looks like we've got 4 Phillips screws on the front here and maybe a 1/4 inch one on the back is all. So let me just go ahead and take that one out since we've got it back here now. And I won't show all of this to you. You don't really need to watch me take screws out of a machine, so we'll skip ahead. And we'll set this face down for now. Get the last screws out, and we'll see what this looks like after all these years. So you're seeing it as I am for the first time. All right, well, look at that. Okay, this is very clean inside. May have a few little crumbs on the bottom of the case, but the inside here looks very clean. I like that. I don't see anything burned out. Looks like we've got the oscillator coils here, and power transformer right there, filter capacitor here, and probably I would say that's the audio output transformer sitting right here. And we've got 2 tubes in it. One of them, well, they're both 12 AT7s. This is V1, and that's V2. And the variable capacitor. Change the frequency. And as I said, the filter capacitor, looks like we have a 2-section filter cap here. I'm not sure what the value is. I'll have to look at the schematic. But one thing I'm really interested in finding is if that filter is leaking or not. And just looking down here, it doesn't appear to be leaking and doesn't appear to be bulged in any way. So I might just test that, and when I get done testing it, if it tests okay and has a low ESR, I might just go ahead and leave it. Probably put a line fuse in there at some really low value in case it does decide to short in the future and it won't take out the transformer, which I'm sure is a piece of unobtainium on that. So yes, this is looking real good. I think I'll go ahead and do some resistance tests here, and just to see if what these resistors are like, and if they're out of tolerance or how far out of tolerance they are. And we'll start with this first one here. It looks like this is a 1,000 ohm. That's where I'm pointing to. See what that comes out to be. Like 1,000 ohms on the money. Now, you're probably wondering, hey, Dean, is it really accurate if you're going to test them in circuit? Well, what I've found is, especially on tube circuits, that if the resistor changes value over time, the resistance will go up. So if you run into a resistor that the value is out of tolerance, say it's supposed to be a 1,000 ohm resistor and it's up to 1,200 ohms, you can bet that resistor is bad, because even if you had something in parallel with that resistor in circuit, the resistance should go down. So if you're getting a higher reading, it will be way out of tolerance. So you can always bank on that idea. Got another one here. I don't know if we can see that on camera or not. That's this one right here. Might have to tilt that down a little bit so you can hear over. And that looks like a brown, gray, yellow. So that'd be 180K. Does that sound right? Let's see what we got here. Looks like it's 197K. Okay, and that's a good example of what I was talking about right there, is that this value has gone up over 20%, because it has a silver band on the resistor. It's 5, 10, 20. So, and it's over 20%, I think. Yeah. So that is way out of tolerance. So even if there was something in parallel with that, resistance would even be higher. So that one will need to be replaced. So what I usually do is I go ahead and mark those with a black dot if they need to be replaced. And then we can quickly go over some of these other ones. Here's one here that is, move the camera over there a little bit. This is brown, red, yellow, so that should be 120K. And it's 125, so that's well within tolerance. And there's one up here. It's brown, black, brown, which should be 100 ohms. That's easy to figure. 20% of that would be 120 ohms, and it's showing up as 124. So it is a little out of tolerance on that one. It's beyond the 20%. So we'll go ahead and go through this and see how many of these we need to replace, and come back later and I'll show you what we did to it. But in the meantime, I think since everything looks good inside here, we're going to go ahead and fire it up and put it on the variac and dim bulb tester and watch it real close and see what happens, just to see if the thing, just to make sure we don't have a bad power transformer or something else, shorted filter capacitor or something like that. So let me get set up for that, and we'll continue. Well, we've got our device plugged into the dim bulb receptacle there, and we've replaced the 200 watt bulb that I normally use for larger draw devices with this a 100 watt bulb, which will light up even quicker if there's more of a short. This signal generator does not really use a whole lot of current, so I suspect the dim bulb won't even light up. So we'll go ahead and turn on the variac here, and I'm going to slowly start rotating this voltage control up, and I'll be monitoring the AC on this meter here, and I've got our DC meter right here plugged into the filter capacitor so we can monitor the DC voltage. And power switch is turned on. The RF attenuator is up about to the 50% position. We're on band A, which is somewhere around 100 kilohertz on the band here. And we've got our oscilloscope plugged into it, so when this comes active, if it does, we should see a display on there. So I'm going to position the camera here to where we can kind of monitor the filament lighting up on one of the tubes here and the B plus voltage. And looks like we're already at 1 volt. Now this has a solid state rectifier in it, so we're going to see DC voltage right away, and I think that's what we're seeing here. That now that I turned on the variac, there's just a minute amount of voltage going into the signal generator. So I'm going to dim the lights down here a little bit so we can see the scope a bit better. So I'm going to go ahead and advance the variac a little bit right now, and you can already see we're getting DC voltage because of the solid state rectifier, and we're up to 12 volts already. We're going to do this a little slowly, just not to so as not to shock the filter capacitor. I don't know how long this has been turned off. I'm sure it's been years. Right now we're up to about 20 volts on the AC voltage, and you can see it's producing 56 volts DC on it. Nothing showing up on the oscilloscope yet, so we'll go ahead and advance this up to about 70 volts right there. And we'll leave that set for a moment. Let's take it up to about 80. Oh, and looks like we have a signal already. It's producing. Let me adjust the sweep on this. See if we can get that to lock in. Yeah, okay, there we go. Now we've got looks like the signal generator is working. It's putting out a signal all right. And we're going to advance this up to, right now we're at 90 volts. And we're producing 115 volts DC in the power supply. Let's just go ahead and take it up to 110. And nothing on the dim bulb yet, so I think we're safe in what we're doing here. And let's go ahead and let's take this up to 120 volts. That's full voltage. Full line voltage.
If I push it any harder, the whole thing will blow.
And looks like we've got a signal here. It's not the greatest in the world, but it does change frequency as I move the knob down here. You'll see that. See what happens when we switch to a higher band. Okay, and now you can see on the oscilloscope Still working on band B. Let's go to C. A little bit of reduction in the RF attenuator. I'm going to turn that up a little bit. Looks like that's working okay. B plus still 150 volts. And of course we can see the tube lighting up there a little bit. Okay, let's take that to band D, and even better output on D. I'm not sure why that is. Looks like my meter's about to shut off here, so we're gonna reset it. The only thing I don't like about some of these newer digital meters is they time out too quick. And we'll change the sweep range here. There we go. That's a very nice sweep we're getting there now. Still adjustable. And let's go to the last and final band, the E band. And you'll notice that the frequency really hasn't changed any. The output level has. It's up all the way right now. But there's virtually no difference in frequency there. What a lot of generators will do is just use a harmonic of the previous band, and that way they don't have to generate the higher frequency. I think the E band here goes up to, looks like high as it'll go is 14 megahertz, which is pretty high for this technology. And yeah, looks like we're good to go. We still have good DC voltage and a good signal. So what I think I'm going to do is set this up a little bit here so we can look at the front while we make a few little adjustments. Looks like when I adjust the modulation, that makes a little difference on the scope there and amplitude. Let's turn on the sweep and see what happens. Okay, you'll notice quite a bit of difference on the way the scope looks. So apparently, I think this thing is actually sweeping all right. Right here. So if we switch it to external sweep, that shuts off, and internal, there we go. If I just switched it to internal, you can see the difference there in the way this acts. You can see the modulation change there. So, okay, so we're on internal modulation now. So it looks like all the functions are working fine on this, and I don't see any reason why we need to go too much further with this segment of the video. So I think I'll go ahead and start testing the rest of the resistors and see which ones are out of tolerance, and I'm going to go ahead and replace those out of tolerance ones and test the capacitor, filter capacitor back here, and if that has a problem, I'll change it out. But if not, I think I'll just leave that in there and put a fuse in the line just in case it should short someday. So I'm going to go ahead and turn this off and end this segment of the video. One thing I wanted to correct here was my statement of using a harmonic when going to the upper bands. My old psychogenometer would do that, but this one does not. I've got this thing set right now on the E band, as you can see, and we should be reading around 10 megahertz, and I'm looking on the frequency counter and it is around 10, so I'm going to switch it right now. I'm going to switch it to the F band, which should be around 28, 29 and a half, something like that. And we're at 28.2. And so this actually does put out the frequency that it states on the dial. It does not use a harmonic on the higher band, so I just wanted to correct that. Okay, we are finished replacing some of the resistors in here that were completely out of tolerance, and they're more than I thought it would be, 3 or 4 of them anyway.
Let us hear it for our poor dead friend.
As you can see here on the schematic, I marked them. What I did here was I'm just going to replace some of these that may be critical to the function of the generator. Some of them that are not critical I left in there, such as this 100K resistor. It's out of tolerance, but it's just a current limiting resistor for the neon power lamp, so that's not critical at all, so I left it. But that's all I could find that's wrong with this thing, other than the power cord here was in pretty bad shape. As you can see, that had to go, and I replaced it. And while I was replacing it, I also inserted a miniature ABC ceramic fuse, just in case the filter capacitor or something else should short in the future. It'll pop that fuse instead of taking out the transformer. The capacitor, I thoroughly tested it for leakage, ESR, and value, and it is just fine. Reads like a brand new one. So I'm going to leave it in there for now. I kind of like the way it looks, and I don't know if I want to go to all the trouble of recapping or rebuilding that capacitor, so I won't do that. And we also tested the tubes on this. There's 2 of them in here, V1 and V2, and as you can see on the schematic, they are 2-section tubes, and those test just fine. They're just simple triodes, dual triodes, 2 of them in each tube, and tested those. No shorts, no leakage, have good emission on them. And one thing I wanted to caution you, when you're working on something like this and you pull the tubes out, you really want to get them back in the same socket as they came out of. Even though they're the same number, they will have slightly different characteristics, and you will throw the calibration off a little bit. And you want to keep it as closely calibrated to the original as possible. So we got them back in the same socket, and they are original RCA tubes. So I noticed that on the schematic and in the manual that this device was probably built around 1975, if you're wondering about the year it was produced. Okay, so the first step in the alignment here is to do the mechanical part of this, and that is to align the dial with the scale. And so there's an alignment mark right here, and I'll show it to you as best I can. It's right below the F, and there's a little mark right there. I think you can see that, and I'll highlight it in the editor. But what you want to do is close the tuning gang all the way closed, and then align that to the mark by changing the set screw in the collet right here. And this one is already lined up, so there's no problem with that. And we can go ahead and continue with the rest of the electronic alignment. That's the only thing right now that we need to do mechanically, is to get that in the closed position and right there. So let's go ahead and continue with the electronic alignment. Before we begin the calibration procedure, there are a few tools you'll need to do this. And number one is some alignment tools. You'll need one that has a screwdriver blade end on it, common one. You'll also need a plastic hex alignment tool for the coils. And this is also a standard blade plastic screwdriver also. You will also find very handy a frequency counter, a vacuum tube voltmeter, and an oscilloscope.
Shoot, a fella could have a pretty good weekend in Vegas with all that stuff.
You will also need two crystals, a 10.7 megahertz crystal and a 455 kilohertz crystal. Now, if you're like me, you probably don't have all of this stuff. So I'm going to show you how to get around a lot of this. I do not have the crystals, but I know of another way I can do the alignment on this, and it will work out just fine. So I'll show you how to do that now. The first step is to adjust the sweep linearity before we do anything, and that is done doing adjustment using R9 here on the schematic, and this will adjust where the center of the sweep frequency is. So we will start out with the 455 kilohertz band, and as you can see on the front of the signal generator here, that I've got this set to 455, and I apologize that it's upside down. It's just a lot easier to video what we're going to do on the other side of the panel here. So we've got it set to 455, and we'll come over here and see if we can keep these things straight. And what the directions say to do is to adjust R9 so that the signal of the generator coming out, get some of this moved around. Now I'm going to have a little problem with the blanking of my oscilloscope, so I'm going to have to wait until this comes back around so we can see the whole trace. Now, since I don't have a 455 kilohertz crystal, I do have a tiny SA, which is a sweep generator, and I should say a spectrum analyzer. That's what SA stands for. Now, I've got this set to generate a signal. I've got it set to put out a signal of 455 kilohertz exactly. And we're going to pipe it right in parallel with the output of the signal generator right here. And from there on, we will go around and go through a demodulator probe. Now, if you're not familiar with a demodulator probe, what that will do is it will take out all the RF content of the signal and just leave a DC content. So you can use a oscilloscope of any kind, even an older one, and actually an older one works better, so you can see the scan rate. Now what we're going to do is we're going to set the scan to 2 milliseconds, and the input to, right now it's at 20 millivolts, and that's about it, really. This 2 millisecond scan comes out to about 60 cycles per second. So as you can see here, now that I've got the Tiny SA generating a marker, we can go ahead and adjust R9 to where we will center up the trace or the mark right there. Now I can turn this on and off, and I'll show you the difference, how this mark comes out. And again, we're going to have to let the camera shutter sync up with the scope again. I have no way of adjusting it on this camera, so we'll just have to wait. Okay, you see the trace coming in now. This is the beginning of the 455 kilohertz sweep. So it's actually probably around 355, scanning up and over 10% and back down. So you're seeing the sweep right there. And I'm going to turn this off. That's the marker, and then back on again. Now with it back on, we're going to go over here, and I'll show you where to adjust this. It's this pot right down here. Get a little light on it so you can see a little bit better. And we're going to adjust that to where that marker will be right in the center of the sweep. Okay, now we got that whole thing right there. Let's go ahead and turn R9 until it centers up right in the center of the, let me adjust this position here a little bit so it's better or centered. There we go. Now we'll adjust that right to the center, you see. And now we can see that the marker right here is directly in the center. So we know we have this linearity adjustment on R9 perfectly done. Now, if you don't have a marker generator or a crystal, the directions say you can go ahead and attach your vacuum tube voltmeter right to that center lug of R9. Get it over here a little bit better. Right down in there. And adjust it to where your VTVM reads exactly 6 volts. And sure enough, it's right in the center of 6 volts and right in the center of the mark on our screen. You can barely see it there. And that's completes that step. Now for the rest of the alignment, we're going to have to go ahead and put it in the case because it will affect the adjustment. Anytime you work on a signal generator or a device doing alignment, you'll always want it in the case because the metal does react with the frequencies that are being generated. So let me go ahead and put it back in the case, and I'll show you how to do that. Okay, and I also wanted to mention that you can adjust the center mark of the sweep using L7 and L8 inductors in the back of the signal generator. Now they were very nice, and they put a little cutout here that and inserted a little knockout so you can get to these with while it's in the case, which you want to do. And so I've got my tuning wand into L8 for the FM part of it. And as soon as the sweep comes back around here again, I'll show you how that adjusts that. But you'll want to do this for both the 455 kilohertz range and the 10.7 megahertz range for your FM band. Okay, our sweep is showing up again. So what we're going to do is we're going to center up the mark on here by adjusting this. And looks like we've got it right in the middle now. If you can see it a little better, but you can see as I turn this, it moves that mark one side to the other. And so we'll just put it right dead center. And again, you'll want to do this for both the 455 kilohertz band and the 10.7 megahertz. setting here on the front of the generator. Okay. Now let's go on to the alignment of all the bands on here. And we're only going to do one because the process is the same for all of them. So we'll just do the one. Well, now that we've got the cover in place and all the screws inserted and down tight, we have our equipment hooked up, and I'll show you what we're doing here. You'll notice I have a T down here at the RF output, and I'll explain that in a minute. But the signal cable goes up to the frequency counter right there, and all our equipment's been on for 15 minutes. On the front of the panel here, we have the VFO turned on. The sweep is set to external. We don't want any sweep in this. The crystal oscillator we're not using, so it could be low or high, it doesn't matter. And I've got the RF turned up to high here and the attenuation all the way up. And so all our equipment's been on for 15 minutes and is nice and warm, and I'll show you how to go through the alignment procedure. We're only going to do one band, so that won't take us very long here. And I'll also show you an alternate way to align this, just in case you don't have a frequency counter, which up until a couple of years ago I didn't either. So there's another way you can do it using a radio receiver, shortwave or AM broadcast band. Either one will work, and I'll show that to you right now. First step is to, of course, we wanted to get our tuning gang closed and aligned with the witness mark right here, as you can see there. That way we know all the mechanics is in place, and we're going to go to band E, which is the red band on top here, and we're going to set this at 5 megahertz. And as I said before, the procedure is the same for all of these. And what you do is you start with the low end of the band at 5 megahertz, and then center your frequency, changing the inductor L5. Then we'll switch to the high end of the band around 14 megahertz and adjust the capacitor C5, and that way the scale will be nice and linear. A lot of frequency counters do not do this. They only have one adjustment, and that's for the whole band, and that this is really nice. So we've got this set up, and I've got my alignment tool in the right inductor. I know it's hard to see here. Let me get a flashlight and I'll show you. It's way inside there. And they're in kind of a half moon shape inside the device here. And let me reposition the camera a little bit so we can get a better view of this. Okay. Now, as I said, the inductor L5 is in, has the alignment tool inserted. And let's go up here and look at the frequency counter, and I'll start turning this alignment and see if we're going the right way or not. No, we're not. Let's go back. We need to go up to 5 megahertz. And get as close as possible to that 5. That's pretty good right there. I don't think I'm going to get much closer. It's pretty touchy when you get down to that 4th digit. Okay. Now, when that's done, we'll go ahead and turn it around here. And we'll take it up to 14 megahertz on that same band. So let's just turn this up to here to 14. We'll see how close we are at the high end of the band. Okay, I'm looking right at 14. And as you can see on the counter, it's 14.2, so it's off a little bit. Let's just go ahead and turn this around, and what we'll need to adjust is C5, which according to our pictorial diagram here will be the first adjustment going clockwise on the capacitor here. So that'd be this one right here. We'll see which way to turn this. Okay, I'm going to try to do this with two hands. We're going to turn this up. There we go. Now we're getting close. Taking quite a few turns here, so it's out of adjustment. It's been out of adjustment quite a bit. There we go. And I think we'll stop right there, since we'll have to usually have to do that procedure a couple of times. Now we'll go around to the front again and take this back to 5 and see if we change the adjustment on the 5 again. Right at 5. And believe it or not, it is very, very close, 5.005. So I don't think we're going to get any closer than that. So this band is finished. And as I said before, all we need to do now is go through the rest of the bands doing the same thing with the frequency counter. Now, if you don't have a frequency counter, I'm going to show you a little trick that I learned a long time ago. It's called the zero beat method. And what it involves is a radio receiver, preferably a shortwave radio if you have one. If not, you can use an AM receiver on this. And let me turn the radio on and we'll tune it into 5 megahertz, which is WWV in Fort Collins, Colorado. And it's we know that frequency is exactly 5 megahertz. So let's go over there now. We'll turn on the radio, tune it in. And it's going to be very weak because I'm shooting this in the middle of the afternoon, and there's a snowstorm going on right now, so it'll still work. You can barely hear it back there. There we go. Now what we'll do is we'll come back here while that's playing through, and we'll see how close this dial is. Okay, we're at 5 megahertz, and as promised, I was going to show you what this T was doing, and all it is a little antenna that I'm using to send the signal over to that radio. So basically it's just a wire coming off the T right here. So now as we rotate this, you can hear that squeal, and when it zeroes out, that's called the zero beat. So these frequencies are exactly the same. And if we look up here on the frequency counter, we see that it is 5 megahertz exactly. So that technique works really well. You know that frequency is right then, and if you look on the dial, we are exactly, see if I can get my thumb over here, exactly 5. Guitarists have known this, and musicians have known this for a long time, that when you beat 2 signals together, when you get that 0 beat, everything cancels out, and so you know you're exactly in tune. So works for guitars as well as radio equipment. Now you can also use the AM band on just a standard radio station, and if you know the frequency, for instance, we have a station here that is exactly 10 on the dial, and so you can 0 beat your generator against a station like that, and adjust your coils and capacitors on this so it will 0 beat to that signal. And it doesn't have to be a strong station. As a matter of fact, a weaker one works better. And when you get the 0 beat, you're right on the signal. You don't really need a frequency counter. And another nice thing about it is you can use harmonics. For instance, if you need to detect a signal of, say, 1 megahertz, tune that into your a 1 megahertz band on your radio to a station there, and you can go lower and adjust your frequency, your signal generator to 500 kilohertz, and use the harmonic off of that, and it will beat against that 1 megahertz signal on the radio. And the same way you could go down another step to 250 kilohertz and on and on. So that's a sneaky way to get around not having a frequency counter. So I hope this helps you, and I'm glad you're with me through this whole thing. It's been an enjoyable process working on this. It's a very nice unit, and maybe somebody can tell me how to get rid of these marks on the front here. I'm not sure what to do about that, or I don't want to take off the silk screening here, but it's starting to look a little corroded. So if anybody has any idea, just leave them in the comments there. And once again, thanks for watching, and we'll catch you in the next video. Bye for now.